we have today with us Dr. Taylor.
Right.
Dr. Taylor is going to tell us about something related to his work.
I'll tell you about something that Pau hates, and
I don't hate it. I just find it irrelevant.
Okay.
No, I'm joking. But by the way, just try not to move so much because you are consuming a lot of data.
Okay, I will minimize my movements. Okay, so I'll start. I want to actually start by showing my screen. So let's see if this works.
Oh my goodness.
Okay, maybe this isn't going to work. Man, oh, that's fine. Like that. Can you see this?
Yes.
Okay, you probably can see even the side tab.
Live streaming is on.
Okay, so so you can see this galaxy right in the middle of the screen, right? Okay, cool. So just to check, it's not just Pau there, other people are there too, right?
Yes, I can see it.
Okay, so I do insist everyone interacts because it won't work otherwise. And I'm gonna keep probing you all, okay? So that's how I wanted to do this. So let's keep sort of like a chat. So this is the galaxy that's, it's pretty close to us. So it's a well-studied galaxy, okay? And this is what it looks like in optical light, okay? And it's basically a spiral galaxy. And that's this optical light that we're seeing is a thermal emission, and I'm going to come on to what's thermal emission and what's non-thermal emission in a second. But let's look at the same galaxy now in non-thermal emission, and what I want to get across is that it looks very different in non-thermal emission. It's a bit of an abstract picture, this, because what you're seeing here are contours of radio brightness around the galaxy. But the point is that the emission that we're seeing from the non-thermal particles is coming from different parts of the galaxy from where the thermal emissions are coming from. Okay, so that's the backdrop of my talk about what we're seeing here for the radio is coming from the non-thermal particles in the galaxy. What we saw in the previous picture, in this one here, is coming from thermal particles in the galaxy. And I want to talk about, introduce thermal particles and non-thermal particles. Okay, that's my aim. So let's see, how does Chrome do this? So if I stop sharing the screen, is that easy to do? Can you see my board now again?
Yes.
Yes. Excellent. Okay, great. So let's move on to thermal particles. Okay. So let me try to start off by drawing. I'm going to do lots of plots on the board, sketches. Okay, so let me try and draw a sketch here. So this will be.
Try to make it very big, Andrew.
Yeah, can you see that or not?
Yes.
Yeah, I'll keep it big. I know you like it big, Pau. Yeah, I'm going to be plotting the distribution of particles. Okay. This is, I'm putting the particles into energy bins, okay? And this is something that's probably familiar to you, that you've seen before. I'm doing a thermal particle distribution. So basically, I'm just doing a Maxwellian, okay? In fact, technically, I should have been using momentum and not energy, particularly when I'm talking about the thermal particles, okay? And well, it's a familiar distribution to you all, I guess. The point is that the particles are all talking to each other. We'll talk in a second about how this is actually coming about. What's producing this this emission? This distribution. Okay.
Wait, Andrew.
Yeah.
What is P times dN dP, etc.?
Okay.
Slow down.
So what we're looking at here is we're looking at particles in the system and looking at the momentum of the particles, and then just binning that momentum into momentum bins. So here we would have like bins of momentum on the x-axis, and then see how many particles are in each momentum bin, and then basically this would be some sort of histogram here, right? And then if I make the histogram very small, it would be this distribution. And in fact, I typically would do this on log scales. For thermal particles, that's not so relevant, but for what I'm going to come on to, well, I'll do all my plots in log space.
Okay, but these particles, where are they coming from? Where are they? What is it supposed to represent? Is this a galaxy? Is this what kind of system? What is this?
This is just like the particles in your room, right? So they're in thermal contact with each other, so they're colliding with each other, and they're in thermal equilibrium. And we're getting our Maxwellian, and this peak energy of here, p squared, okay, over 2m is basically kT, right? So this is I thought would be familiar territory to start from, and then I wanted to ask the question. Actually, start off by saying, well, why the exponential cutoff? Yeah. Maybe we could have a think about why we get an exponential cutoff when we have a thermal distribution of particles. And I thought a fun way to do that, or to consider that, is to start off in a particular state. Okay, so let me just start the whole thing off again with another plot. I presume you can see. Yeah, you can. Right. I'm going to put all of the particles in the same. Okay, I'm going to now insist on plotting it in energy and not in momentum. But you've got the principle. And I'm going to put them all in the same energy state, these particles, in my box. Yeah. And I'm going to put the box, so I have a box here of particles moving around the box, right? And colliding with each other. Yeah. And then reflecting off the walls, they can't escape. So all they can do is basically collide with each other. And I'm starting them off, but it's all in the same energy state. So I guess my question to you all is that a stable configuration of particles?
But so this is a thought experiment.
It is. A lot of my talk will be thoughts experiments. I thought that would engage a bit. So yeah.
Yes.
So
okay.
So let's talk. So firstly, does it sound very stable configuration?
Thermodynamically.
Yeah, exactly. Will it stay like that, or will it change?
Well,
another way to put it is, does it sound like a very low entropy? Does it sound like a low entropy state or a very high entropy state? Is it very likely that they've all got the same energy?
If you know that we're looking at your ear, right, the left one. If you want.
Well, it's my best ear, so that's why. You shouldn't see my ear.
I mean, if you want to talk to show your face, you should rotate your face by 90 degrees.
Yeah. Okay. Like that. The staring at the camera is kind of weird.
Oh yeah, don't worry. But okay, so I know I guess I know the answer, but I'm not supposed to reply, right?
Yeah, no, I want everyone. Come on, guys, you're all there. And don't be worried about making a fool of yourself. I mean, I'm not. I know you're not.
Yes, but what about the rest of in particular, Cuban people? Come on, this is for you. Cuba, come on. Silence.
Hi, I'm sorry, could you repeat your question?
Yeah, sure. So I've started all the particles. I have an imaginary box, and I put particles in there, and all that they can do is collide with each other. And I put them all with the same, every particle exactly the same energy as every other particle to start with in my box. And my question is, does that sound a very stable configuration?
I think it should be. It should stay like that.
You think they'll all stay with the same energy exactly?
If there are only elastic collisions, yes.
Yeah. Okay. Well, then I will update that it's not a very stable configuration. It's actually a very low entropy state that they're in. And what they're going to do is they're going to collide with each other and go into a more stable configuration. Okay, and you can do this.
Andrew, are you asking from the global point of view, or just you were asking if each of the particles is going to stay with the same energy?
I'm talking about the global point of view. So when I plot like this here, this is of all of the particles in the system that I've binned.
Okay.
Okay. Yeah. So of course it's elastic. So every time the energy of each particle, of the two particles, will be conserved every collision. But then there's lots of different collisions and momentum exchanges that they can undergo. So the global configuration will change. Okay, so what will happen? Sorry, does someone want to say something? No? Okay, so, well, one way we can think of it, right, is let's discretize the energies of some particles. So let's just do a load of particles, right, and start them off with some particular unit of energy, right, like 100. And I'll put them all exactly the same energy, right? And they're gonna, and then the energy which we discretize, they're gonna shuffle their energy backwards and forwards. So, you know, one unit of the energy will shuffle to another particle, etc. And you just keep repeating. And what you've got going on is really like a diffusion of energy process. You get, to start with, you'll get, for a few time steps, you get a Gaussian around the initial configuration. That Gaussian smears out more, okay? And then eventually, what we're going to get, actually, I'm going to change the representation and just do dNdE, not eDNdE. And eventually what I'm going to get is my Maxwellian, okay? So it's going to relax to a Maxwellian, and that is going to be in a stable configuration. And so why did I want to go through that? Is another. Well, actually, I'll tell you what. Not only, okay. So the reason I wanted to go through that was to say that's all very good for particles that collide with each other, like particles in your room. But in astrophysics, the collision times, and let's think about what the collision times are of particles next. Okay, so does anyone know? So, you know, particles in the room. What does anyone know what the density of particles in your room is that you're sitting in, roughly? No? Just roughly?
Come on, people. Someone, come on. This must be interactive. And Andrew's a very nice guy. Well, don't ask Basu, but he's a very nice guy.
Okay. Let's take it one step at a time.
1 gram per cc, roughly.
Okay, that sounds like the density of water, Basu, but I like it.
I mean 1 per cc, sorry.
So what's the density of air compared to water? Does anyone know that ratio?
Can you try to improve your Spanish accent?
Mine?
Yes.
Okay, ¿qué es la densidad, like comparisons dentro de la densidad?
De un vaso de agua.
Yeah. Here's my bad accent.
No, just to make a Spanish accent. You are too British. It's difficult to understand you. So what is the density of a glass of water? Is this what you're asking?
No, Basu's told us that. And then we said, well, we want to convert that to the density of air. Okay, so we remember.
Is it 1,000 or 1 million?
Let's say 1,000. Okay, thanks. Okay, so, and then we remember that, I mean, we've got a proton being about, what, 10 to minus 24 grams. So this guy is what, 10 to 24 per centimeter cubed, and this is 10 to, so there's 10 to 21 centimeter cubed is air, right? And then if we, So our collision length is 1 over n sigma, okay, and sigma t is the Thomson cross section. So we've got 10 to the 21 centimeter cubed for air, but in astrophysics, the densities that we're typically dealing about in extragalactic space are what? What's the typical density of the interstellar medium?
What is the interstellar medium?
Okay, even if I go out into the solar system and sit there in the solar wind outside the Earth's atmosphere, what's the density out there?
It's not a glass of water.
1 atom per cubic centimeter.
Yeah, that's a very good reference number. 1 per centimeter cubed is actually a little bit higher in the solar wind, but I don't really care. So the interaction time, right, is going to be 1 over nc. Well, they're going to be moving at non-relativistic speeds, maybe. So we have a velocity here instead of c. But when we put in 1 per centimeter cubed, what we get is an interaction time of something like a mega year. Okay, so in astrophysical plasmas, our scattering times, collisional scattering times, are phenomenally long. And in fact, we don't get into thermal equilibrium in astrophysical plasmas typically through collisions. Okay. Okay. So, in fact, what we often see in astrophysical plasmas are non-thermal particle distributions. So now that we understand a thermal particle distribution, let's go into the solar wind again and catch particles and bin them like we were doing before, right? And now I'm doing a slightly different representation, p squared dndp, but it's not very important. Okay, and what we see in solar wind is we see our Maxwellian distribution of particles here, and then we see our non-Maxwellian distribution. So this is our non-thermal particles, okay, and our thermal particles. And it's been wondered why, or considered why we get that non-thermal particle distribution in some astrophysical plasmas.
But, sorry, Andrew, can I? But am I also allowed to ask questions? First of all,
of course you are. Yeah.
Okay, thank you. It's a silly one, but why the thermal part of the distribution is not symmetric around the? Previously you drawn the nice Gaussian representation that was relaxing with time.
It was relaxing. It started off symmetrical, like you said, but it becomes actually asymmetric as it relaxes, because ultimately it's phase-space distribution. It's going to fill up in phase space. So in phase space, so dn d3p and d3x, it's going to become. It's going to get its exponential cutoff, right, like we said. But then it's going to go down to 0. Okay, so it fills in phase space, and so it becomes quite asymmetric. And then, of course, here I'm plotting p squared dndp, and that gives you this how steep, and that's going to steepen it even more here.
Oh, thank you.
So it starts off symmetric, and then as it feels, actually, it's very interesting because if you think about it, a Gaussian is actually e minus x squared. But then as it starts to feel 0, that's when the exponential cutoff kicks in. I even did a little animation for you if you want later. I could show you. Or
yeah. I never thought of that like this.
Yeah, it's nice to. I really wanted it to be more like a discussion like this, actually. So let's see, how's that going to work? So if I share my screen again. Here we go. Okay, can you see that?
Yes.
Okay, so there we go. So here we start off as a Gaussian, and then it starts to feel 0, and the exponential cutoff kicks in there. Okay, that's what I was trying to say.
Okay.
Right, so let's go back to Okay, back at the board, right? So, okay, so that's so far so
Andrew,
good.
sorry.
Yeah.
Can you explain what you mean by here field zero? That's like maybe I don't.
Oh, right.
Right.
Well, they were spreading out in energy space.
Right.
And remember, what I did when I did that problem was I discretized my energies and started to shuffle them around. And
Right.
as eventually they can fill all the way down to zero, and as they fill all the way down to zero, we get this very okay.
Okay, thanks.
So the next part of the problem I want to consider is kind of similar to that problem that we just considered, but now I want to. Now we're wondering how we can get a non-thermal distribution of particles, and actually this is an idea that Fermi came up with in the 40s of how we can do this. So let's repeat the experiment, but now I want to have a two-particle system. I want to have some massive macroscopic particles, and I want to have some microscopic particles. Yeah. Okay. My massive macroscopic particles are moving around at low velocities, and in fact, I'm going to put in my microscopic particles at rest. Okay, so it's kind of it doesn't sound like a very stable configuration, right? So what will and let's I'll draw it up here. What will my particles do next? I'm only going to bin these small particles. So I'll do a momentum distribution of these small particles with time. And what do you think they're going to try to do?
Andrew, I'm getting complaints that it's very small what you write. So you have to do it even bigger.
Bigger. Okay, sorry. That's fine. Okay, I'll do it down here. Maybe it's better to see it down here. I'm doing what I did before, which is just a plot of the
Thank you.
momentum distribution. So starting them off cold, okay. Maybe I'll start them off cold but non-zero, just as a little delta down here of particles, of these little dots. And then they're going to try to do, those little particles. And when I say so I should probably explain a bit better. These massive particles have got very big mass. These little particles have got a very small mass. And there can be orders of magnitude between the small particles and the big particles. So what will the small particles try to do?
They will try to hit the big ones, but then they do not move because they are too heavy, and then there is there's relaxation that it was before.
Yeah,
but
exactly.
Cheating because you know this weight. What about
Yes.
What about the rest of them? Sorry, I mean, Octavio, I didn't want to bother you.
No.
But Cuba, say something. Say something. Are you following? Diana, Benny, Joel, Miguel.
Jose.
Yes. Are you following? Don't give us silence, please.
Yes, I'm following.
Diana, yes, wonderful. What? Say something.
I'm having a hard time trying to understand the board. I'm getting low definition image. So
Also, you cannot see the board well. So you see that Andrew has a big and a small particles, and he was asking what? Andrew?
Yeah. So starting off I'm sorry, my pictures are so crappy. I tell you what, I'll share my screen because I even made a nice picture of it for you. So, and that might help a bit. I only wish I was better at using this thing. Okay, but I'll get better with time maybe. So you can see that picture then?
Yes.
Okay, so that's what I'm talking about now. I'm starting off those little red dots, with very low momenta, right? The big blue dots with a large amount of momenta. And what do you think the little red dots are going to try to do? And they're all in in a box with reflective boundaries, the particles can't escape.
What about now, Kuba? Diana, can you see this?
Yes, I can see this.
Okay, and did you understand the question? It's fine to say no. Or you can say something.
You can tell me that my pictures are crappy, don't worry.
Yes.
Hi, your picture's fine. Could you repeat your question again? Sorry, I'm having
Okay, so
trouble with the connection.
okay, so I've got this system set up of now it's two types of particles in the system. These big macroscopic particles and small, actually elementary particles, and the small elementary particles, I'm starting off with very low momentum compared to the big macroscopic particles. What will the small, I would like to think about the evolution of my momentum distribution of my small elementary particles. What will they do?
So the question is, what are going to do the red balls?
Will they increase their momentum due to collisions?
That's right. They're going to try to get into thermal equilibrium with my big macroscopic particles. They have, and actually, so Fermi's paper on this was very charming and simple. And you can think of it, they have the audacity to try to get into thermal equilibrium with a macroscopic object. It's a strange, well, I find it a strange idea, right? So let's plot it. They're going to start off with this low momentum distribution. They're going to start to spread out as they. I'll do plots with time, maybe not with this pen because you can't see it so well. Do that. Okay, and then their momenta will spread out more and more and more. Okay, and in fact, what we're talking about here is called stochastic acceleration, because these small elementary particles are trying to get into thermal equilibrium. Maybe this is interesting to Ottavio, you're here, right?
Yeah, sure.
Yeah. So they're symmetric in log space. I thought you might like that.
Yeah.
Okay, then look, these are log normal distributions that you get for this type of problem.
Andrew.
Yeah.
Andrew, sorry, can I interrupt you? Could you try to speak a little bit more slowly? Because,
Sure.
Okay, thank you.
Okay, so I was just saying that, so remember my plots are always in log space when I'm plotting them, and they're staying symmetric in log space. And what I'm plotting here is the first time step, second time step, third time step. Okay, in fact, I think if I remember, I even made a plot of this, a numerical plot of this for you. So I'll quickly, I'll show you that so you know what I'm talking about, maybe a little bit more accurately. Yeah, so here I'm showing you.
Andrew, sorry,
Yeah.
can I just have one, maybe it'll be helpful for some of us if you can also give a physical example of where this happens, so to develop an intuition of what is the macroscopic particle here and what is the microscopic particle.
Sure.
So we can.
So in Fermi's original problem, he was considering balls of plasma with magnetic fields embedded, and each ball of plasma was moving in it with a velocity direction which was independent of every other ball of plasma. Okay, and these balls, like I said, are macroscopic, so you can think of them as little magnetized clouds. Okay, and the little particles are protons, let's say. Okay, so perhaps not truly elementary, but certainly very small, and they're scattering off these big macroscopic clouds and having their energies eventually boosted.
So
Okay.
like in gas clouds and things like that.
Yeah.
Okay.
Exactly. So that's the picture, and it's a simple picture, and it can give you this very energetic particles that was, it's the pursuit of this. The problem being attacked is how to get particles up to very high energies. So it does satisfy that goal. The problem though is that is the shape of the power law that it can produce. Stochastic acceleration has a problem that it's in some ways it's got too many degrees of freedom. The spectrum that's produced is not going to give us this flat spectrum that we see in astrophysical space, sorry, in plasmas. In fact, we can get any shaped spectrum that we like. Okay, so in its first application, it's a good first step, but it's not quite good enough to give you the simple flat power laws that we see of the particles. Okay, so it needs to be applied to a slightly different, in a different setting to get to work. And let me write down for you the problem. So I'll try to explain. Okay, what stochastic acceleration is going to give us, okay, is a power law, okay, of this form. Can you see that?
Yes, but what are the two? Yeah, there are two times, right?
Yeah, there's T acceleration and T escape. Okay, so my particles are trying to get into thermal equilibrium with the other fluid, but eventually there's going to be an escape time of those little red dot particles that we were considering, the small particles, and so we have an injection term. We're injecting deltas at low energies, an escape term, and we can get into steady state in the system. The problem is that we can get any shape power law we like, right? Unless the acceleration time happens to balance the escape time. If the acceleration time balances the escape time, we can get p to the -2 type spectrum, which is what we actually typically see in astrophysical plasmas. So the question is, why, or in what situations put us into or have the relationship that T acceleration equals T escape? Okay, so this moves us on to motivates us to consider shocks. Okay, so this is a little bit of a change in direction now. I want to talk to you about what are shocks, and in some ways I want to say, what do they do? What do the shocks achieve in life? Okay, so let's.
But you mentioned thermal particles, right?
Yeah.
And then you mentioned non-thermal particles. And you're moving to shocks. Well,
Yes.
What is the connection between
There is a
these?
connection. So this is where you need to pause your question a little bit, because I'm going to talk about collisional shocks, and then I'm going to talk about collisionless shocks, and then you'll see the connection at that point. But at the moment, there's too many pieces, and I leave them suspended, if that's okay.
So you promise that I will see the connection?
You will see a connection.
Okay.
Okay.
Andrew?
Yeah?
Can you maybe do a summary plot of the spectrum that we observe with this Maxwellian and the power law tail? I don't know if you showed it, but I saw it on your slides. But I assume that's a good summary on what you just discussed.
Okay, sure. I'll do that, Mark. So here's the slide that Mark's asking for. It shows the Maxwellian part at low momenta, and then the power law tail at large momenta. Okay, and it's this that we're trying to connect to or to explain how that can come about. Okay? Is that okay, Mark?
Yes, perfect. I mean, to me it's clear, but I think it's
no, it's good that you say this. Okay.
Mark, is
I
it clear
also,
to you?
sorry.
Wait, Mark, is it clear to you?
What do you mean by clear now, Pau?
I don't know, you said it is quite clear to me, so I'm asking you, is it clear to you? Could you make a summary, because I got lost.
Okay, so as far as I understood, we have this Maxwell. So if you observe the universe, we don't only have the Maxwellian part, which Andrew was motivating in the beginning, but we also have this non-thermal tail, which happens to be to have this power law slope. So the spectral index of it is around 2, and the question is why and how do we get this? And what Andrew was saying about that one idea, the idea of Fermi was to think of these clouds, big balls, having a much larger momentum than the small balls, and so that they, by time, translate their momentum to the small particle, and the question is now whether this can also give us the right power law slope or not. And Andrew was saying that this is not entirely not that determined, and I think that's why he wants to introduce shocks now, because they have a quite convenient mechanism.
Okay.
Yeah. Sorry if I'm being too fast, but let me just put that in the corner here then, so that you don't lose track of that. Maybe I am leaving too much suspended. Okay, so here's the plot that we got. Okay, and this part here has dn dp going like p to the minus 2, right? Which is what we observe. And then what we found from stochastic acceleration, right, was that we could get any spectrum that we like.
Can you also draw like a reference scale for the momentum, where we are supposed to observe this thermal part and the non-thermal tail?
Yeah, absolutely, sure. Okay. Of course, it depends on the plasma that we're talking about, but let's talk about a good reference case might be the heliosphere, right? Because that's just on our doorstep. So let's just step outside the Earth and think of, and we'll just step outside the solar system, okay? And in fact, it's a good example case because it's also a place where a shock occurs, okay? So let me start off by reminding you what is the heliosphere, okay? We've got the sun here, right? Of course, it's shining off its radiation, right? Which you all think about. Probably what you don't think about very much is that it throws off a wind as well, okay? And it throws off that wind at a velocity of about 10 to the minus 3, the speed of light. Yeah? Yeah, follow me, guys?
Yes. So you're talking about the solar wind, right? Yeah.
Exactly. So we've got this wind being thrown off by the sun. Okay. In the near region around the sun, the pressure of that wind is a supersonic wind, and it's the pressure of the system is the ram pressure of the wind. So the velocity of the wind is the dominant pressure in the system, and of course it's going to drop like 1 over r squared, and it does, until it gets into pressure balance with the interstellar region outside of the solar system. Okay. And when that happens, and I wanted to come on to that next, but to answer, it was Ottavio, it was you who asked the question, right?
Yeah, it was me, yes.
So to answer this question, Ottavio we have to ask ourselves, well, when that wind, that ram pressure, goes through the shock. What's the temperature of the region out here? And the answer is it's this velocity over c squared times the mass of the proton, okay, is the temperature of the plasma produced downstream. So there's a reference number for you, Ottavio. So 10 to minus 6 times a GV, so it's about a kV temperature.
Thank you.
Okay, so that's a reference scale. But actually, so that's a little bit ahead of us. I wanted to talk more about a shock, because I actually wondered if you've thought about shocks and the different types of shocks, because of course the shock that you might be familiar with is a shock of around a jet plane that's moving supersonically through the air, or a meteorite coming into the atmosphere. So they're both examples of collisional shocks, because so let's just quickly describe a shock. Okay, we have the upstream here and the downstream here. Okay, here's the fast velocity material coming in from the upstream, and slower material in the downstream, and we're in the rest frame of the shock in this plot. Okay, are you following?
Yes.
I am, but I guess I'm not the one you're asking.
Okay. Okay, well then, if people are following, tell me then, why is the wind, so this is V upstream and V downstream, why does the gas slow down as it goes through the shock? Can anyone answer that?
Yes, it doesn't make sense, right?
It seems strange, right?
Yes.
Okay, I'll tell you what I'll do. I'll give you one way to think about it. So let's think about the pressures in the system. Up here, right, we've got rho V squared, rho V up squared. That's ram pressure. And then in principle, we have P thermal. But I'm going to make it a cold shock. So this is going to be very, very cold, and basically there's no pressure there. Okay? So if you think about how the pressures are distributed in the system, they're not very well distributed in the system. In fact, it's quite an unstable configuration. You've only got the pressure in the ram pressure, and there's no pressure in the thermal particles. Okay? And then when in the downstream, we're going to have, of course, a ram pressure in the downstream. So maybe ups and downs for the density is the difference in the upstream and the downstream, and the velocity is the difference. Okay, but this is the ram pressure in the downstream, and then there's a thermal pressure in the downstream. Okay, and so does anyone know why the gas is going to slow down as it goes through the shock? And what are shocks good for? What do they do?
Maybe I can make a guess. I don't particularly know, but is it the fact that the kinetic energy is being used in the thermal motion as opposed to the net translation?
Yeah, that's exactly right. Right. So a nice way to think about, a way I like to think about it, is that the degrees of freedom are being stimulated in the downstream. So it's going to distribute its energy and its momentum downstream in a more fair way. In the upstream, it was very unfairly distributed. And then what the shock is good for is to stimulate the degrees of freedom that were not stimulated in the upstream. Okay, so that's why it slows down. It's robbing the ram pressure, and it's distributing that to thermal pressure. Okay.
Okay, cool. Thank you.
Always. Okay, so and that's what shocks are good for, right? So essentially, that's all there is to know about collisional shocks, right? But like I said, that's not what shock physics in astrophysical context is like. This is a collisional shock. There's only thermal pressure and ram pressure to worry about, okay? And Okay, so let's go on. How then, if I'm in a collisionless plasma, yeah, how am I going to get thermal particles in the downstream of a shock in a collisionless plasma?
Sorry, Andrew. Just one question. Maybe it's relevant to the other students. I don't know if they know exactly what ram pressure is here. So it's difficult to probably have this intuition what the thermal pressure is competing against. So if you can just give two lines on what ram pressure is.
Okay.
Because I'm not sure if they are aware of ram pressure. That's why. That's all.
Okay, sure. So the ram pressure is the big coherent global scale motion of the gas, and then there's of course you can find a frame where the motion of gas is isotropic, and that component of the pressure is what we call the thermal pressure. Okay, so there's the coherent flow is the ram pressure, the incoherent flow is the thermal pressure. Okay, so like we were saying, what the shock's doing is it's robbing energy from this coherent flow, and it's just isotropizing it to make the thermal pressure downstream. Is that clearer?
Yes, thanks.
Okay. So for a collisional shock, right, where the particles are banging into each other, like on Earth, right? Jets, supersonic jets, or meteors coming into the atmosphere, the thermalization is going to happen through collisions. How will it happen in a collisionless shock? Can anyone have a guess what might happen? It's not an easy question, this, by the way. It's quite hard, actually.
Maybe could you, because I'm trying to think about it, maybe could you give me a better picture? Because when you say collisionless, okay, the precise definition of this is what?
Yeah, fair. That's a good fair point. So collisional is where there's very small scale electric fields happening when the two particles are coming into very close proximity with each other's charges, right? Mm-hmm. So we'll call that collisional. And collisionless is where that can't happen. The probability that we're going to see each other's Coulomb fields is just way too small. So we can define a length scale, right? So our scattering length, right, is 1 over n sigma, right? And we can create a scattering time from that too, right? And the system might have an age. So let's think of well, the heliosphere is a good example. It's a good one that I like to come back to. So we said that if the density of gas in the astrophysical settings is 1 centimeter cubed, the collisional time is like a mega year. Particles stay in the heliosphere for at most month timescales. There's an advection timescale that they can't stay for longer than. So certainly they can't hang around for mega years. So they have to have another agent to thermalize the shock. Okay, and that's. What, do you have more of a think about it, or?
I mean, I'm wondering what interactions are left. I mean, there's maybe photons involved, but that's also electromagnetic. So I'm not sure.
Oh, well, you're on the right track. It's electromagnetic is the answer, but it's not photons. It's okay. I'll tell you then. It's magnetic fields. So the in the downstream, and like I said, it's not an obvious thing. You'd be hard pushed to try to guess this stuff, in fact. But the in the downstream, other degrees of freedom are going to be stimulated, and one of those are magnetic fields set up by currents in the downstream that are then going to act as an agent to isotropize particles and thermalize downstream. Okay, so So the difference between a collisional shock and a collisionless shock is the agent, is how they thermalize. In the collisional shock, they thermalize through collisions. In the collisionless shock, they can thermalize through little magnetic fields. Okay, so I went to the efforts of making you a lovely picture for this. So there we go. Okay, so that's the picture I want to paint for you.
Can I ask what shape of a magnetic field? Well, it looks like in the picture that we have different directions of the magnetic field.
Yeah.
So I'm wondering what shape of a magnetic field will. Oh no, I guess if you have many different magnetic fields in different directions, this will thermalize the plasma. Okay.
Yeah, but fair enough. Good question again. So what we can. So I'm going to just come back to the other screen again. Right. What we've got going on here is, like you said, isotropic movement of these magnetic waves, and this is magnetic turbulence, in fact, right? So it is sort of at least semi-isotropic, because it's got to be distributing the particles quite into an isotropic distribution. Right. Let me just remind myself. Oh yeah, right. So, but magnetic fields during the isotropization, they change the rules completely of what can go on, because we said at the beginning of the talk that the particle I started particles off with a little narrow distribution at the very beginning, right, where I had all the particles starting off in with the same energy in different directions in a reflective box, and the particles spread with time. Oh, and I wanted to say something about that. So I thought a good way to think about that is that they've got, equal, what's the word? Opportunity, equal opportunities, not equal opportunities of outcome, but equal opportunities for where they can go. All particles can get into the high energy tail, and all particles can go into low energies. But when you have got the magnetic field doing isotropization, low energy particles and high energy particles can do different things. And the reason for that is that when you've got the magnetic field, you create a potential barrier at the shock. So let's do. So here we have the shock in the upstream. And then the downstream, and we said it's moving at different speeds. Okay, so down and up. Okay, and there's a magnetic field associated with the shock. I'm going to put the magnetic field in this direction, so B up and B down. Okay, and yeah, because the magnetic field it's moving at different velocities in the upstream and the downstream, we're going to create a potential barrier between the two flows. For low energy particles, they can't ever hope to get back up into the upstream region once they've been thermalized. There's just no hope. But if you've got high energy particles, okay, in a magnetic field, they've got Lana radii in that magnetic field, and they have the possibility to go back up into the upstream once they can get past that potential barrier, which the low energy particles can't. So it's like a two-tier type of society, which is set up by the system. Okay. Okay. So I wanted to then focus on what do the particles that are able to go back into the upstream, the high energy particles. What will they do? What will they do next? Okay, so I have this idea of drawing the upstream particles and the downstream. Okay, the downstream particles are going to be spaced denser than the upstream. It's slowed down. So rho, the density has gone up, the velocity has gone down, and so these are the background particles in my plasma. Okay, some of the particles that have been thermalized can have a sufficiently large amount of energy that they can leak back into the upstream. Okay, they can go into the upstream, they can bounce around, and then go down into the downstream. They can bounce around, and then they've done a cycle. Okay, and this is the connection to the Fermi process that we said before, but with a slight difference. In the Fermi process that we said before, the acceleration time and the escape time were disconnected, so we could get any power law slope that we liked. For this type setup, and there's a velocity difference between the two flows. So we said here we have a V up and a V down, right? We have an energy difference, so we'll do one cycle. Okay, so the energy that particles get for one cycle is going to be something like V, this energy difference, so we'll call it delta V, something like this for one cycle. Okay, so delta E is the initial energy of the particle times 1 plus beta per cycle. So that's the energy gain that they'll get. But they're in a flow, so they're coming from the right and then going down to the left. And they can only, even if some of the particles are able to diffuse back into the upstream, they're still in an advective flow. So eventually they're going to be leaking out of the system. So we're going to get a loss of the particle number is going to be changing every cycle and going down. Okay? Of these lucky particles that can leak back into the upstream after they've thermalized in this collisionless shock. Okay, so what we can appreciate, I think, are people following?
People, you're supposed to reply. Come on, come on, come on. Jorgo, are you following? You can, but are you following? I know that you're here.
No.
Is that a yes or is that no? Andrew.
Yeah, one sec. I'm spinning out the power, so I'm just going to grab a cable quickly.
Yes, Jorgos is not following you. He did not understand anything.
Okay, sorry. Then I will try to do a better job. So, Jorgos, where did I lose you?
This is a question for you, Jorgo. So can you start from the beginning, Andrew?
Okay. Yeah.
I'm joking, of course. But Jorgo, can you be more precise? What is that you did not understand? And what about the rest of you? Okay. Look, Andrew is making an effort, and he's really trying, as you can see. So please ask questions, because this is the point of this meeting. Especially for the Cuba people, you can see that the guy is sweating and moving and kneeling and writing the whiteboard. So go ahead and ask him, because it's important, I think. Otherwise, well, he can keep on talking, and he will not get, I don't know, we will not get anything out of this.
Well, if nobody else has a question, I am stuck on one thing. I'm imagining thermodynamic cycles, and I'm not completely clear why we gain energy in one cycle.
Okay, fair enough. So let's think about how we do that. Okay, So how do you say your name, by the way?
It's so it's an Irish name. It's Kian, as if with K.
Yeah. Thanks, Kian.
Kian.
Okay, right. So let's do. I want to imagine Kian. I'm going to put. This is in the rest frame of the shock. Okay, V up and V down. Okay, and if we just for completeness, I'll put in the numbers. The V down for a monatomic gas is going to be equal to 1/4 times V up. Okay. And that's in the rest frame of the shock. So let's do 2 other plots. Okay. I'm going to do the same plot in the rest frame of the upstream. Okay, so the upstream is going to be at rest, and I'm going to do the downstream. Sorry, this is the downstream. Downstream at rest, and then the upstream at rest. Okay. So if we're in the downstream rest frame, yeah. What velocity will the upstream be coming to you at if you're in the downstream rest frame?
3/4 of V up you should have.
Yeah.
And then
okay.
the particles on the left would have 0.
Yeah. Okay. And if we're in the upstream and we're in the co-moving frame of the upstream, what's the downstream doing?
Minus 3/4.
Right. So it's coming at us.
Yeah.
Okay. So once the particles go across the shock and they isotropize on the other side of the shock, they see the other shock or the particles on the other side as always coming towards them. Yeah. So that's the point, is that they always get an energy boost when they go from one side up to the other, because they get hit in the face, they isotropize in that frame, and they go back down to the downstream again, and they get hit in the face again.
Yeah. Okay.
Okay, so that's why they eventually get an energy, or they get an energy boost every cycle like this.
And so why do they isotropize? Because they isotropize when they cross a shock.
Like you were asking before about this magnetic fields. It's isotropic turbulent magnetic fields. So it isotropizes the particles, and once they're isotropized, they're co-moving in that frame.
Okay, I understand the pictures you have drawn. That's very helpful. Thank you. But if anyone does not understand, you should say it, because it's a nice picture.
Actually, one comment maybe here. When we talked about this in university, a professor kind of brought the how do you say table tennis? How do you say this plate you play it with? And the analogon was that if you let the ball fall on the ground, and as it bounces off, you move the plate downwards to the earth, so that the distance between the two becomes smaller and smaller and smaller. So you kind of can imagine in your head that the ball bounces faster or more and more frequent, and it gets faster and faster and faster. That's kind of a similar picture.
Yeah. In fact, if you really meditate on it, you start to realize that this is very like Fermi's original idea. What the particle's doing is it's trying to thermalize between the two flows. It's seeing an energy difference between the two, or the momentum difference between the two flows, and it's trying to, and eventually, in principle, like your two bats, Mark, falling towards each other, the ball bouncing between them can eventually exert enough force to stop the fall of the two. And particles like here, likewise, it can do that. If they can get enough energy, they can even start to affect the shock, because they can provide enough pressure of their own to certainly distort the shock. And that could, in principle, that could happen. Okay, so let's continue. The particles, every crossing, they get a delta log E, right? Delta log E is constant, right? And delta log N is constant, right? Delta log N is decreasing and delta log E is increasing. So if I do a plot of the energy of the particles, right, with time, what is the energy of the particles going to look like with time?
Sorry, Andrew, there's a question in the chat where someone is asking, what are shocks?
Right. So I think we said that before, that what are shocks? In a short answer is they are places where the upstream is thermalized downstream. So they're machines that thermalize a flow, right?
But in general, are they just any discontinuity in a macroscopic property of a flow?
That's right. Yeah. So that, of course, in truth, it's where the velocity has a jump in it, but that velocity jump has happened because it's thermalized. So you can say like a definition, and you can measure the density everywhere in the space and say, oh, there's a big jump in the density, ergo there's a shock, right? Or you could just look for thermal particles, or you know, in the downstream region and say, oh, look, I'm seeing thermal particles. There's an engine that thermalizes particles. I'm seeing a shock. And in fact, sometimes we do see shocks from the thermal downstream signature of the shock. But, okay. Does that answer the question?
I guess who was asking? Joel, I guess that was your question. So does it help? Maybe you can reply.
Yes, thank you.
I'm not scary, by the way. You can talk. Okay, so we have the energy. The delta log E is going like a constant every crossing time. So how is the energy going to change with time? Anyone?
Get what?
Sorry?
What are you asking?
So every time they do a crossing, the logarithm of the energy gets a constant boost. So how will the energy change with time? Can you think of an expression, I don't know, like of the form E equals as a function of time?
Still don't answer previously.
Should it go up with the exponent?
That's right. It's exponential growth of the energies. So the energies are going to go up with time. Sorry, this is not energy. That's a bad plot. Energy with time. And what about the particle number? What will that do with time?
It will correspondingly decrease exponentially.
Yeah. Okay. So we get a drop of the number and a growth, and those two are in perfect sync. In fact, what you find is this gives you this e to the minus 2 type spectrum in the source, and that's fundamentally because the acceleration time, right? This acceleration probability links to the escape probability, right? So you can see that this lower one is basically an escape probability. This up one is an acceleration probability, and they've got the same, well, the 1 plus and 1 minus, but that's the thing that's being plus and minus is the same value. Okay, so that's basically what we've got here is an application of Fermi's original idea, but in a place where we get, and naturally leads to an e to the minus 2 or a p to the minus 2 type spectrum. Okay, here I'm using e's because I'm always thinking relativistically, but in reality you should be using momenta for the low energy particles as they're not relativistic yet. But the principle is that you get a p to the minus 2 type spectrum because the acceleration time and the escape time are linked. Okay. Okay, there's any questions on that? Okay.
I haven't understood the total lecture. How can I make up them? I'm sorry.
So what did you say?
Sorry, okay. I just haven't understood total.
Okay, I don't know then if I can help you, because so you're saying you've understood nothing. Okay, well, I'll just shall I just continue? But unless if you want me to help you, you'd have to explain what I've not explained clearly, and then I can try and fill in the gaps.
Pardon? Oh, I'm sorry.
Okay. Okay, so what I wanted to talk about next, or to go through is because ultimately I want to say what are cosmic rays, or what are these non-thermal particles? What are they good for? All we've discussed so far is how they can be brought about. We said that shocks in extragalactic space are collisionless. The application of our Fermi acceleration process to astrophysical collisionless shocks, or can be applied to this setting, and gives us naturally a p to the -2 type spectrum, which is like the one that we observe. Okay, but I've still not really answered the question, what's they good for? So do that.
Sorry, Andrew, one more question that might be interesting for everyone. So these kind of shocks in astrophysical systems, where can we observe them? Will the sun have it? Will it be?
Yeah, I talked about that earlier, the heliosphere.
Yeah, no, but what I mean in terms of Fermi acceleration, where else people can expect, so that they can relate it in their picture, apart from sun, what other systems can we think of, or something to link this up? I think so it might be just difficult to visualize this physics and visualize it in terms of astrophysics. Maybe that's helpful.
Okay, so well, the sun was one example because it throws off this fast wind. Another example that we can think of is a supernovae, when a star dies and it throws off this fast material. That material is moving supersonically, and eventually that's going to get into pressure balance with the ISM and set up a shock. So there's another example.
So like
every time we throw off gas at a supersonic speed, we set up a shock.
So like the bow shock, we have the nice pictures we always see of the bow shock in the heliosphere and all, on those kinds of shock.
Not okay, true. Except we don't know that there is a heliosphere has a bow shock. But, okay,
right. Okay.
Let me just bring everyone into the picture there. But so what Vasu is talking about, what I'm talking about, are not quite the same thing. I said that this is the sun and it's throwing off its wind supersonically. There's a termination shock of that wind. Okay. Of course, in the downstream of the termination shock, the gas has still got a velocity, and there's a discussion about, so this is the sun, and the sun's moving in this direction, and this is the ISM out here. Okay, this is the upstream, right, of the flow. This is the downstream of the flow, and then this flow here might also be supersonic compared to the ISM temperature, in which case this here it would be a bow shock, but we don't know if that is actually a bow shock or not. But certainly every time we've got supersonic flow, Vasu, into an astrophysical plasma, we've got a shock will be set up, and then these processes will take place.
Cool, thanks.
Okay, so let's see. We've got the particle. These particle populations will be set up, and then how will they move around? So we've discussed that a little bit already, haven't we? About how the particles are going to move around. But let's discuss that a little bit more. Okay, if the magnetic fields in astrophysics were just big coherent magnetic fields, the particles wouldn't be able to move anywhere, right? They'd stick to the field lines. And that's not what happens. I think we talked about this earlier, that so here we have a big coherent magnetic field in a particular direction. Then we'll have this, I'll put them as wiggles, magnetic field, okay, moving in other directions. So this is my turbulent magnetic field. And what's going to be, every time my particle is moving along the field line, it's going to be deflected a little bit by the turbulent magnetic field, and its pitch angle of the particle in this magnetic field will be deflected by this little magnetic wave that comes through the system. Okay, so you can imagine if these delta B's are coming in isotropically on top of this big coherent field, the pitch angles of the particles start to random walk. Okay,
Andrew,
yeah?
I think you have to explain what the pitch angle is.
Okay, right. Great. So we have a particle with momenta, P, right? Is our particle moving in a magnetic field, B, okay? And there's an angle here, theta, okay? And basically, theta is describing the pitch angle of the particle. Okay, so it's of course the P in the Z direction, sorry, P in the B direction is conserved, and the P orthogonal to that is also conserved, but the particle does helical motion around the magnetic field. Okay, but this angle, the pitch angle, if the magnetic field is coherent and stays at the same strength, the pitch angle will just be preserved. It won't change. If there are little magnetic waves coming through the system, however, the pitch angle will change, like I just described. Okay, so we'll get our pitch angle changing by the ratio of the perturbing field to the guiding field. Okay, and that'll change the pitch angle by a small amount, and then this process will be a random walk type process. So eventually we can work out the timescale that it takes the particle's pitch angle to completely isotropize, to start off. It can start off with one particular pitch angle and then random walk to be any pitch angle. Okay, and we'll call that the scattering time. Okay.
Sorry, can I ask a question?
Yeah.
Why do we have a guiding field here?
Right. So this, what I'm describing here, is called quasi-linear theory. So it can help to describe what's going on, and then certainly the description becomes harder when there's no guiding field.
Okay.
In the shock situation, there is something of a guiding field because there's a global magnetic field of the system. If you think that let's imagine, for example, the heliosphere. So the magnetic field around the sun is this Archimedes spiral magnetic field. So it's got a global structure, but it's also got its noise on top of that structure. And you can think of that, Kian, as or an analogy would be to think of velocity flows, where you've got big coherent velocity flows, but on top of that, turbulent motion in the flow as well. So your question's a good one though, because some situations your guiding field will basically be will be irrelevant. It won't really be there, and you'll be in a fully turbulent type of fluid or plasma.
So here we treat sort of a magnetic noise. Okay.
Yeah, exactly. Okay, so we can work out the scattering time, which the time it's going to take the particle to fully lose memory of its original pitch angle. Okay, so yeah, it's what that time scale will be. We want to every scattering is going to deflect by delta theta. Yeah, we want we're going to call upon the random walk result. Okay, so delta theta squared, sorry, maybe I should have called this little one small delta theta. Okay, the big delta theta squared is going to go the number of scatterings times small delta theta squared. This is calling upon the random walk result that the width of your Gaussian grows with theta sigma squared grows with the number of events. Okay, so overall we're going to get we want to work out when this is large. Okay, and this is going to allow us to work out our scattering time. Okay, so and why do I take you through this? Because sorry, I'm trying to keep track of what I'm trying to get to. Oh yeah, we want to work out how the particles are propagating. Okay, so the pitch angle starts, so the momentum directions random walk with time, and eventually are isopropized, and that gives us the concept of the scattering time. And then the particles' spatial distribution starts to evolve with time as well. Okay, so that should be quite familiar to you. If particles scatter randomly every time step, what will be the distribution of particles around an original distribution? If I start particles off as a little delta in space, how will they evolve if they scatter randomly thereafter?
A Gaussian function eventually.
Right, as a Gaussian. Okay. So what we're looking at here is the distribution in space, okay, of particles around, okay, our around our initial position. I use dt to describe the sigma of the Gaussian. Okay, and d is basically relates to the scattering. It is just the scattering length. Okay, so we start off sort of like we did before. We have a delta distribution. This is now x, and this is dn dx. Okay, and our particles spread out with time, right? This might be familiar to many of you. So our particles are random walking away from the source of the particles. Yeah. So this is as a function of space and of actually of time. Okay. So so that's how we inject a delta in space and delta in time of particles, and that's actually, this is now the Green's function of how the particles then propagate. If I keep repeating that, what does the distribution of particles around the source look like? So let's think about the expression for that. That we just integrate out the time variable, okay, of our Gaussian. Okay, and what will this look like, or does this integral even saturate? Does anyone have a feeling for that, or can you see that? Anyone?
I have a feeling this converges.
Okay, why do you think it converges?
With t. Sorry, I was looking at the x. In that case, diverge.
That one's divergent, right? And so there's a physical reason why it's divergent, okay, let's go with the physical reason. So this result here, we're thinking of 1D diffusion, because whoever told me it's a Gaussian, I presume that they meant it's a 1D Gaussian, okay, which is what I've written here. the problem with the 1D Gaussian is the particles, there's no growth in phase space. So the particle moves away from its origin, it's 50-50 whether it turns back or goes or keeps going, right? So in the 1D random walk type problem, there's you're going to return to your place of origin an infinite number of times, and the integral's not, so that's the physical one. And they can even, another way to look at it, just look at the integrand. This guy here is going like 1 over t to the half, and then we're integrating over t. So you can even get the feeling how it's going to diverge. That's if it's in 1D space, but if it's 3D, then that's 3 halves here. Okay, and now is it going to converge or diverge now?
It should converge because you will not return to your original position in 3D space.
Yeah, very good. And what about 2D?
I have a feeling something weird happens in 2D.
Yeah, it's the tipping point one, okay, where it doesn't quite converge, but it nearly does. Okay, but let's do the 3D case. Okay, so if we do the 3D case, we have the 3 halves here. What we find is that this goes like 1 over d to, sorry, I'm going to change variables from x to r because I'm doing 3D. Okay, it goes like 1 over dr. So if I have a source of non-thermal particles, a source term, and I keep injecting at the source every time step, and they random walk away from where I inject them, and they're allowed to random walk in 3D space, they can build up a steady state distribution. They can actually escape. It's quite funny to think that they get to steady state just because of the growth in phase space. And they build up a 1 over R-type profile. And this brings me to what the question was I was asking at the beginning of what a cosmic ray is good for. So cosmic rays build up around their source in a particular way, in a very different way to the way that particles that move, say, ballistically or in an advective flow move away from their source. Okay, where that would be 1 over R squared type propagation. Okay, so number 1, the particles build up around their source would be the first answer to the question of what a cosmic ray is good for. And then so I wanted to come back to this concept of the heliosphere, okay, because it's an interesting thing to think about. Okay, so the sun, of course, is throwing off lots of radiation. Okay, but if I think about the ionizing radiation that the sun throws off, okay, its X-ray luminosity is something like 10 to 28 ergs a second. Yeah, and its wind luminosity is something like 10 to 27 ergs per second. So these are much smaller than the thermal radiation field luminosity of the sun. So if we think about what will the X-ray energy density around the source is going to be 4 pi r squared c. Okay, the energy density, if there's a source of cosmic rays with a similar energy to the energy density of the wind, 10 to 27 ergs per second, the energy density of the cosmic rays, okay, is going to be dr. See, so the building up of this is basically a re-expression of what we said before. The particles are building up around the source, okay, and therefore they can start to become a very relevant ionizing agents around the source, particularly further away from the source where the X-rays have started to diminish. Okay, so that's where cosmic rays can be important. And there's another difference about cosmic rays and X-rays. So let's think about how an X-ray and a cosmic ray ionizes. So an X-ray, does anyone know how an X-ray ionizes the gas?
I don't want to say something every time. Anyone, please feel free to interrupt me, but I imagine it just when colliding with the electron or electron cloud, it provides it enough energy to escape, and then you have the split up nucleus and electron.
Okay, that's one way it can sort of Compton scatter like you're talking about. Even before that, at slightly lower energies, it can liberate electrons through photoelectric absorption. That's got quite a large cross section, but and let's stick with photoelectric absorption because that's got the large cross section.
Okay. Yeah.
Okay, so our X-rays come through, they photoelectric absorb, and then they die because they've been absorbed. Okay, so the important thing is the interaction length. Okay, for the X-rays. So Lx interaction is going to be 1 over n sigma. Okay, where sigma is our density of our plasma. Okay, of the electron or the atoms that we're going to ionize. Okay, what about that's the interaction length. You can also work out the energy loss length, but for X-rays that's going to be the same as the interaction length, because the definition of the energy loss length is the same as the interaction length with this factor K, which takes into account the fraction of energy given up in that interaction. Yeah, so that's the loss length for X-rays, and we can do the same for the loss length for cosmic rays or for these non-thermal particles. Okay, so okay, and we're just going to do the loss length, and it's going to be the same expression here. Okay, and so the important thing is how are the cross sections different, and how are the inelasties, the fraction of energy given every collision, different. So the cross section, well, photoelectric cross section is quite a bit bigger than the cosmic ray ionization cross section, which is something like much more comparable to the Thomson cross section. But the important thing is the factor K in these two. That's the energy given up. When the X-ray ionizes, it gives up all of its energy to the electron when it's liberating it. The cosmic ray, being a very energetic particle, subsequently gives up a very small amount of its energy every ionization process. So it can undergo many ionizations. And so if we think about it, I've said that the energy density around our source of cosmic rays, or around our shock, really, the ionization, the beginning will be X-ray dominated, but it will quickly be taken over by cosmic rays, because A, they drop off more slowly with distance away from the source, and B, they when they're ionizing, they can undergo many ionizations because of the large amount of energy that they carry. So now coming to the conclusion, what a cosmic ray is good for? They're very good at converting energy or taking energy and taking it a very long way from their source and then dumping it at large distances. So that's more or less the bottom line. It comes back to that picture that I showed at the beginning, where you had the galaxy, this large galaxy, nearby galaxy, and you could see where the thermal particles were, and you could see where the non-thermal particles were on top, and they've gone much further out than thermal particles. And the principles of why that is exactly what I'm talking about. That they carry energy far away from where they're born, and then eventually dump it there. Okay, so that's more or less what I wanted to go over.
Andrew?
Yeah?
You still have to time integrate the diffusion to get the 1 over r dependence, right?
Yeah. We just said it in words, but that it went to, when we time integrated it, it went to 1 over dr in the 3D case.
So I'm just thinking of the shock picture. If the shock is fast enough, like if the shock is faster than the diffusion. So to get this result, we have to assume that the shock is slow. The time scale of the shock is slower than the timescale of diffusion, right?
Mm-hmm. Yeah.
Okay, yeah.
Yeah.
I
So
mean, for the galaxy, that's probably not a big issue. But if you, I don't know, I'm thinking of the relativistic shocks. That might be interesting.
Right. Yeah. So for relativistic shocks, the particle's going to, well, their source term is going to be moving very quickly with time, indeed. So that's a slightly somewhat different setup. The principles are going to be the same, though. That the particles, that the shock, that this fast fluid is still going to dump a lot of its energy into non-thermal particles and magnetic fields, and that those non-thermal particles are still going to go some fair distance away from the source. So the principles will be the same, but certainly the maths changes because the source term is moving quickly with distance over time.
Okay, yeah.
So I think I got the story you're trying to tell about how this energy is carried so far away, and these pictures at the beginning make sense. Now I am wondering what we can do with this. For example, I noticed that one of your research interests is in dark matter detection, or maybe not the actual detection side of it, but indirect detection, something like this. And I'm wondering, do these processes help us in any way that you're aware of, or is it more like this is an interesting thing and it may help us, but we don't know how?
Right. So is your question then, Kian, that what's the connection, or how does this at all connect with dark matter at all?
Well, that's one thing I would personally be interested in, but more generally, this I guess is the explanation for a mechanism of how this energy gets far away. Is there something about energy getting far away from the source that is particularly useful for us in our observations? That would be the general question.
Right. Well, so let's think of how some of the ways that we look for dark matter. Okay, one of the ways that has been unfruitful over the last 20 years has been looking for gamma ray signatures of dark matter. That the hope that the dark matter is self-annihilating and then gives rise to gamma ray lines. And we look for those lines. And of course, if you're looking for gamma ray lines, you need to know what the background is of, what else gives rise to gamma rays. And as I've tried to convey here, cosmic rays give rise to gamma ray emission. In fact, we've become pretty good at understanding the gamma ray emission from nearby objects. And the good news is that there's nothing that gives rise to really clear gamma ray lines. So there's no, if we did say gamma ray line, it'd be a good evidence that it's a dark matter annihilation, because it couldn't be confused with much else. But we haven't. I mean, there's been, if you remember the literature over the last decade, some people have talked about seeing gamma ray lines near the galactic center, and that faded, turned out to be a spurious artifact. So but the point is that we have been studying gamma ray emissions from nearby objects and understanding how good an accelerator that they are. I haven't talked about that much here, but it connects to very much what I have been talking about. If I ask the question, let's come back to the solar wind, because I really like it as a concrete example object to understand. The solar wind is the sun's throwing off 10 to the 27 ergs per second of kinetic energy, right, in plasma. And then you can ask yourself, well, what fraction of that energy gets converted into these non-thermal particles? And the answer is actually the similar answer to what we see if it's not the sun, if it's like a supernova explosion or even a gamma ray burst. Whenever we see these fast supersonic flows of gas that eventually thermalize in collisional shocks, they give rise to a big fraction, more than 10% of the energy thrown off goes into the non-thermal particles, which is huge. And we don't understand actually why they're so, this is so efficient of going from one to the other like that. So there's quite, that's in some ways, that's still a mystery to be understood. And so your question, I quite like your question. You said, what's it good? Oh, so can you repeat what you said? You said, yeah.
I'm not quite sure how I worded it, but how does it help? Is there a way in which it helps us in our observations, that the fact that this energy does get carried quite far away from its source?
So what is this good for?
What is it good for would be a short way to say it.
Yeah. Well, I tried to convey that it's good for. It changes the dynamics of the system, right? You're injecting energy and it's taking it out and it's dumping it further out. So it's going to change the pressure setup of the system. And another way to see that is just think of that first picture that I showed at the beginning, where you've got these thermal particles which are all clinging to the disk. We do know that there's a pool of they look like thermal particles out in the halo. There's also cosmic rays out in the halo, and they could be constituting a big part of the pressure of the halo, because they go far away from where they're born like this. So they can, once they start to become a dominant pressure, then they will start to change the system at that point. So that's another way of saying, what are they good for?
Okay, cool. Thank you.
So just one more point on this, because it links to what we've been talking about over the last week or two. Of course, if you think about the galaxy, most people think of hydrostatic equilibrium, okay? And one thing that you should have got across from the talks that you've heard is that relativistic gases don't sit in hydrostatic equilibrium. They can't configure to do that once the relativistic gas is the dominant pressure in the system. So if cosmic rays start to become a dominant pressure in the system on large scales, it's a problem, because it's not a stable configuration. And well, that's a whole other discussion, but I wanted to make that connection because it's a theme that you've heard discussed, and I think it's an interesting connecting point to the other talks.
Yeah, and regarding the other talks, we've been connected now for 2 hours, Andrea. Did we have much more to explain? I guess yes.
No. This is all I wanted to go through.
How? Okay. So besides Kian, right, is your name? What about the rest of you? I would be extremely happy if Kuba asked the question. One question. But similarly, they have some problems with the connection again today. So, well, I think we just, I don't know, have a small break and resume with Carlos.